I'm Preeti from Basic Chemistry Honours third year. Today we will read crystal field theory from the book of Inorganic Chemistry of Pradeep's Publication. Valence bond theory helps us to understand the bonding and coordination compound. However, the theory suffers because it neither accounts for the color of the coordination compound nor explain why some complexes are high spin whereas others are low spin. Crystal field theory, on the other hand, explains successfully the color of complexes as well as their magnetic properties. This theory was developed by a physicist named as H. Bethe and V. Black to account for the color and magnetic properties of hydrated salts of transition metals. Originally, crystal field theory was applied to transition metal ions in crystal field. That is why the theory is called crystal field theory. Chemists began to apply the crystal field theory to transition metal complexes in 1950s, and since that time inorganic chemistry has become an excited field of research. Crystal field theory considers the central metal ion and the surrounding ligands as point charges. Point charges are electric charges that exist as a single point. It is important to note that point charge has neither an area nor a volume. According to crystal field theory, it is the electrostatic attraction between the positive charge on the central metal ion and the negative charge on the ligand that holds the ligand to the metal ion. In brief, crystal field theory assumes the bond between the metal ion and the ligand as purely electrostatic. In case the ligand happens to negatively charge ions such as cyanide ion, bromide ion, iodide ion, the interaction between the metal and the ligand is referred as ion-ion interaction. In case the ligand happens to be neutral molecule, it can be considered to have a dipole moment as in ammonia. The nitrogen in ammonia acquires a negative charge del negative and hydrogen acquires a positive charge del positive. In such cases, the interaction of metal ion with the ligand is referred as ion dipole interaction. The d orbitals and crystal field theory. Since d orbitals are frequently used in coordination compound, it is more important to study their shape and distribution in space. In order to understand crystal field theory, it is necessary to look again at the spatial orientation of all the 5 d orbitals relative to the position of ligands in the metal complex. There are 5 d orbitals and are designated as dxy, dy, z and dzx, dx square minus y square and dz square. The boundary surface of these orbitals are given as one subset of the 3 orbitals with dxyz, dxy, dyz, dzx are similar in shape and each consists of 4 lobes of high electron density lying between xy, yz and zx plane respectively. The lobes of these orbitals lie in between the principal axes. There is another subset of 2 orbitals with dx square minus y square and dz square. The orbital dx square minus y square consists of 4 lobes that lie along the x and y axes. The orbital dz square consists of 2 lobes that lie along the z-axis and donut called torus in the xy plane. It is important to point out that although dz square and dx square minus y square orbitals do not look alike in shape, yet they are equivalent as far as their interaction with the metal ions are concerned. The unique shape of dz square orbitals can be regarded as linear combination of 2 orbitals dz square minus x square and dz square minus y square, each of which is equivalent to dx square minus y square orbital. Since both orbitals dz square minus x square and dz square minus y square have high electron density along the z-axis, and dz square orbital has a large amount of electron density concentrated along the z-axis. Since one of the component wave functions is maximized along the x-axis, the dz square minus x square, and the other along the y-axis, the dz square minus y square, the resultant dz square has a torus of electron density in the xy plane. However, both orbitals dz square minus x square and dz square minus y square do not have independent existence. Section 1.4 Assumptions of crystal field theory. Crystal field theory is now more widely used than the valence bond theory. It considers the attraction between the central metal and the ligands in the complexes as purely electrostatic. The basic assumptions of CFT are following. The transition metal ion is surrounded by a number of ligands with lone pair of electrons. The ligands are treated as point charges. Point charges are electric charges that exist at a single point. It's important to remark that point charge has neither an area nor a volume. The ligands may be neutral or negatively charged species. In case the ligands are neutral, such as ammonia, water, ethylene, diamine, it is the negative end of dipole that is oriented towards the metal ion that accounts for the electrostatic interaction. In case of negatively charged ligands such as chloride ion, oxalate ion, cyanide ion, the interaction between the central metal ion and the ligands is purely, that is 100% ionic. All the 5 orbitals of isolated gaseous metal atom have the same energy. These 5 d orbitals of the gaseous atom possessing the same energy are called degenerate orbitals. If a spherically symmetrical field of negatively charged is placed around the metal ion, all the 5 d orbitals of the metal will be raised in energy as a repulsion between the negative field and the negatively charged electrons of the orbitals. In brief, the energy of the orbitals is raised because of the repulsion between the field and the electrons on the metal. However, the energy of 5d orbitals will still remain degenerate. The electric field results from the influence of real ligands, whether from negatively charged anionic ligands or negative end of the dipolar ligands such as ammonia. The electric field is not spherical symmetrical because of finite number, usually 4 and 6 of ligands involved. In such a case, the d orbitals are not affected equally by the electric field of the ligand. We have also noticed that d orbitals have different orientations and in space, and therefore these orbitals will experience different interaction from the ligands. The orbitals lying in the direction of ligands will experience greater repulsive interaction, and consequently their energies will be raised. On the other hand, the matter orbitals lying away from the ligands will experience lesser repulsive interactions. As a result, their energy will be raised to a smaller extent. In summary, the energy of 5 d orbitals of the metal are split up due to electric field generated by ligands surrounding the metal. The splitting of energy of 5 degenerate orbitals of metal ion into different sets of orbitals into different energies. The presence of electric field of ligands is called crystal field splitting. The number of ligands surrounding the metal affects the energies of the 5d orbitals. It means that crystal field splitting will be different coordination numbers. The property of coordination compounds such as magnetic property and the color of the compound can be easily explained in terms of splitting of d orbitals in different crystal fields. Crystal field splitting in octahedral complexes. In an octahedral complex, the metal ion is at the center of octahedron, whereas the surrounding ligands are at the six corners of the octahedron. Let's consider first metal ion without any ligand surrounding it. In this case, all the 5 d orbitals possess the same energy and are called degenerate orbitals. This is represented by 5 lines at the same level on the left. Let's now place this metal ion in a spherically symmetrical electric field consisting of 6 negative charges. Electrons present in the metal d orbitals will interact repulsively with the electric field of the 6 negative charges. This repulsion between the like charges raises the energy of the d orbitals equally by some amount. Let's now consider the electric field generated by 6 charges placed at the vertices of an octahedron. On the x, y and z axis, it's important to recall that the total charge around the central metal ion is the same, but its distribution is different, and hence the surrounding charge is not spherically symmetrical. An inspection of the figure shows that dz square and dx square minus y square orbitals point directly towards the 6-point charges representing the ligands. These two orbitals interact directly and strongly with the ligand charges. As a result of strong repulsive interactions, their energies are raised. The other three orbitals, dxy, dyz and dzx, are not affected as much compared to the dz square and dx square minus y square. As a result, the energy of dxy, dyz and dzx are lowered. It's important to note that the energy of dz square and dx square minus y square orbitals are precisely equal. It means that these orbitals are degenerate. Similarly, the three orbitals dxy, dyz and dzx are also degenerate. A close inspection of figure reveals that dxy, dyz and dzx orbitals are in equivalent environments in the octahedral geometry. May appears that dx square minus y square orbital is being repelled more or dz square is being repelled less. It's important to recall that dz square orbital is a linear combination of dz square minus x square and dz square minus y square and has also electron density in the xy plane. As a result, both the dx square minus y square and dz square orbitals are equally affected and are degenerate. The pattern of one doubly degenerate and one triply degenerate orbital character of all the octahedral complexes. The set of three degenerate orbital is named as D2G. The origin of this name comes from a branch of mathematics called group theory. The other set of two degenerate orbitals is named as AG, and the origin of this name comes from the group theory. We have noted so far in octahedral complexes, the 5 d orbitals are split up into two sets. One set consisting of 3 orbitals of lower energy, another set consisting of 2 orbitals of higher energy. The energy difference between two sets of d orbitals is called crystal field splitting energy and is abbreviated as CFSC. It is symbolically designated as del note. The subscript note indicates that the complex is octahedral. The actual value of del note depends upon a particular compound and varies with the metal ion, the ligand and the charge on the complex. Some of these these factors we'll discuss later. Sometimes another parameter dq is also used instead of del note. These two parameters are related as del note is equal to 10 dq. Let's consider the approach of ligands as a two-step process. In the first step, the ligands approach the metal ions and produce a hypothetical spherically symmetrical field which repels all the orbitals to the same extent. In the second step, the ligands approach the metal ion and splits the orbital degeneracy due to repulsion to different extent. It's important to note that the crystal field occurs in such a way that the average energy of d orbitals remain the same. In other words, the center of gravity of the orbitals remain constant during the second step. It means that the decrease in the energy of set of orbitals that lie at the lower energy level must be balanced by the corresponding increase in the other set of orbitals. Therefore, if the T2G set drops by 2 units, a balance is achieved. The EG set rises by 3 units. Uh, if the difference between T2G and EG level is defined as del note, then it's clear that the energy of T2G level changes by minus 0.6 del note, while the energy of EG set changes by 0.4 del note. In terms of 10 dq in octahedral case, the T2G level is stabilized by 6 dq, while EG level is destabilized by 4 dq. Section 1.7 Crystal Field Stabilization Energy CFSE for tetrahedral complexes. Imagine a metal ion which is not surrounded by ligands. All the 5 d orbitals of metal ion in such a case have same energy. And this is represented by 5 lines lying at the same level. In the presence of a tetrahedral field, the degeneracy of 5 d orbitals is lifted up as a point first. The two orbitals dx square minus y square dz square become stable and their energies are lowered by 6 dq. Second point, the three orbitals dxy, dyz and dzx become unstable and their energies are raised by 4 dq. The crystal field stabilization energy in tetrahedral complexes can be calculated in terms of algebraic sum of minus dq per electron in E orbitals and plus 4 dq for each electron in T2 orbital. The CFSE for tetrahedral complexes with different number of metal d orbitals in term of dq and del T are shown in figure. The splitting of d orbitals in case of tetrahedral complexes are designated as E and T2 instead of EG and T2G. The subscript G is dropped because the tetrahedral geometry has no center of symmetry. The symbol G is the only used for electric field which has a center of symmetry. Tetrahedral complexes. Two of the most common geometries for coordination number 4 have the tetrahedral and square plane arrangements. A tetrahedral arrangement of 4 ligands surrounding a metal ion can be imagined by placing 4 ligands on the alternate corners of a cube or by placing 4 ligands on the opposite corners of a cube. A tetrahedral complex can be also imagined by removing 4 of the 8 ligands from opposite corners of a cube. The 3 coordinate axes are defined as those passing through the centers of the cube and the center of each face of cube. In this arrangement, the ligands do not directly approach any of the metal d orbital. However, the ligands come closer to dxy and dyz and these zx orbitals that are directed towards the edges of the cube compared to dx square minus y square and dz square orbitals. that are directed to the centers of the faces of cube. As a result, the energy of three orbitals, namely dxy, dyz and dzx, labeled T2 will be raised, whereas the energy of two orbitals dx square minus y square and dz square labeled as E will be lowered. Thus, the T2 orbitals are destabilized, whereas the E orbitals are stabilized. Further, since the center of gravity rule holds, the T2 orbitals are raised by 4 dq and E levels are lowered by 6 dq from the very center. The magnitude of crystal field splitting del T is the difference in the energy between doubly degenerate E and triply degenerate T2 level. The subscript T indicates a tetrahedral complex. It is also measured in terms of dq and is related to del T. Del T is equal to 10 dq. A tetrahedral complex, as mentioned earlier, ligands do not approach any of the metal orbitals directly. In addition, only 4 ligands split the d orbitals. 4 ligands instead of 6 would result in 33% decrease in the field. Thus, the splitting of d orbitals in tetrahedral complexes is much smaller than splitting in case of octahedral complexes. It has been experimentally found that crystal field splitting in octahedral field is nearly more than twice as strong for a tetrahedral field for the same metal ion and the same ligands. It has been found for a point charge model that del T is equal to 4 upon 9 del